Alrighty, we are here for I think day 9. Are we on day 9? Yeah, I'm a little late I think it's day 9, yeah. I was working on part 2. Somebody suggested Union find the crate for yesterday's problem. So I was just taking a look at that before we got started here. I haven't quite finished the implementation. It does give me all of the information I kind of need or want. Let's see if I show this, just minimize that, I guess, for the moment. But it does so in an awkward way. You can either, so you have this union find and you can union by certain things or whatnot. In this case, I'm kind of using the positions and the positions or the indexes in the positions vec as the IDs, which is fine. So we're unioning on those IDs every time we union. In this case, we're taking 10 because I'm still working on the test right now. And then you can either .find or .get. .find gives you the ID of the group and .get gives you the size of the group. But as far as I can tell, there's no way to like iterate over this in a reasonable way. So you get insert, you get size, you get union, and you get and find are by key. And there's no like iter on this, or there's no into iter that I can see, which is just exceedingly awkward, I think. Like you can create this structure from an iterator, but you can't iterate over it. So I don't know. I haven't figured it out yet. Maybe there's an API I missed here, but I'm going to take a look at that after today's and see if I can get that into a working state. I think it's pretty cool because yesterday's problem was definitely like a variant of Kruskal's algorithm, which is a minimum spanning forest algorithm, but we don't really need the whole forest per se. PetGraph includes this algorithm by default. I guess by default is the wrong way to say it. PetGraph includes this algorithm. So there's a minimum spanning tree section of the algo module in PetGraph, which implements minspan tree and minspan tree prim, and minspan tree uses Kruskal's algorithm. So you can throw together PetGraph and do it that way. There is actually just a union find crate, and because we need to do arbitrary checking and stopping and whatever, I chose to check that out instead. So let's get into day 9, and I'll get back to that at some point. So I'm going to add day 8 here and git stash. And having everything on one screen is a little bit awkward, so I'm just gonna create day 9. And let's get into day 9. Movie theater. So we slide down a fire pole into the corner of the playground and land in the North Pole base movie theater. So here's our input, separated list of pairs. Elves are redecorating by switching out some of the square tiles. Some of the tiles are red. The elves would like to find the largest rectangle that uses red tiles for 2 of its opposite corners. They even have a list of where the red tiles are located in the grid. So these are all the red tiles, showing red tiles as hash and other tiles as dot. The above arrangement of red tiles would look like this. Choose any 2 red tiles as the opposite corners. Your goal is to find the largest rectangle possible. So this is like X distance, Y distance, do some math. And then it wants us to do the multiplication, I guess. Seems pretty straightforward for part 1, which scares me for part 2. Let's check. Let's check the input. We have the list of all the positions, and that's it. That is our real input. So let's grab this, drop into part 1, grab what is our answer. Our answer is the largest area of any rectangle, which is 50 in this case. And this seems suspiciously straightforward, which makes me nervous. So we're just going to write this parser here. We're going to end up with like a vec of ivec2s, separated list 1, line ending, separated pair, complete I32, comma, complete I32, parse input, separated pair 1. No, it's not. Separate pair. Separate pair is not the function. It's separated. It's a smiling frog. Import iResult. We don't have ivec2 here. I, generally speaking, just like working with these kinds of structs. These structs are like 0 overhead, effectively. So if we map this, we get AB, or rather we get XY, right? And this is just ivec2 new XY. And then we have access to .x and .y. So ta-da, our parser. And we'll just debug red tiles just for kicks to make sure that our parser is actually doing the correct thing. We could also do input here just for kicks. And we end up with no input left and 7.1 down to 7.3. Perfect. There's probably a way that we can cull these actually. My thought in my head actually is the Manhattan distance the numbers we need? right? Manhattan distance is abs diff right-hand side plus abs diff y. So it's the diff in x versus plus the diff in y, which is really what we need, right? Like this is what I was going to do. I was going to do ivec2 minus ivec2 absolute value. So if we just have that function, we might as well use it. So red tiles, iter combinations, right? Let's do tuple combinations. I've explained why I like tuple combinations in previous videos, but really it's because I like the specificity of either, in this case, tuple combinations, or const generics. It's just that the const generic APIs for this tend to be nightly. So we ended up with AB, and we got A dot Manhattan distance B. And do we need the actual values? No, I don't think so. So we can do element product. Can this fail? Is that what's going on here? Hang on. It's just a U32. Oh, it already adds them together. So I think this might not be what I want because I don't necessarily want, I guess if we want to optimize the multiplication out, we could do Manhattan distance on everything, wait to do the multiplication, and then redo the multiplication for just one of them. But I don't really think we have enough for that to matter. We have 500 values to match up, right? Because what we want to do is not just the Manhattan distance, but we want to do the multiplication here, really. I just ripped the code straight out of the Manhattan distance. And the question here is, we just want the max value, right? Okay, so that doesn't give us the answer. Why doesn't that give us the answer? The absolute diff of ax minus bx times ay minus by. This is the area, right? Is there something I missed in the description of the problem? Find the largest rectangle possible. I assume by area definition, right? What is the largest area of any rectangle you can make? So let's do, I guess, an info here, AB area, before we return this value. Because basically I'm debugging at this point. And we'll get test log test on our test, and we will get skip input up here. So we end up with, maybe today would be a good opportunity to modify the tracing subscriber. See, what is this? 7, 1, and 11, 7 is 24. Let's go through a couple of these and check. 2, 5, and 9, 7. So 2, 5, and 9, 7 is registering as an area of 14, which is wrong, right? 7 and 2. 7 and 2 is 14. Are these inclusive? So this is really, for the area calculation, that plus 1. What is that? 8 and 3? That's weird, but okay. So this is the area. Strange, but easy enough. I wonder if that's an implication of some yet to come attempt to multiply with overflow. Okay, let's get, instead of an I32, these are going to be, U64 or I64 vec2s? No, what is the I64 vec2s? Yeah. And this needs an into because I chose to make these not I64s. So let's just hope that I64 is big enough. My question is, like, is this going to come back to bite us in part 2? Because part 1 was really straightforward. Part 1 was basically get the area, but the area includes +1 on the dimensions. which fine, but anyway. So red tiles, tuple combinations, map over that, get the area. I'll probably just remove this for the moment. So I have no idea what part 2 is going to be. I feel like that was too straightforward for part 1 for part 2 to be any ease at all. So let's check out. The elves just remembered they can only switch out tiles that are red or green, so your rectangle can only include red or green tiles. In your list, every red tile is connected to the red tile before and after it by a straight line of green tiles. The list wraps, so the first red tile is also connected to the last red tile. Oh, so this is an ordered list. Okay. Tiles that are adjacent in your list will always be on either side of the same row or the same column. That's nice. Using the same example as before, the tiles marked X would be green. In addition to all the tiles inside of the loop, all the tiles inside of the loop of red and green tiles are also green. Okay. The remaining tiles are never green nor red. So do we have one big loop? The rectangle you chose still must have red tiles in the opposite corners, but any other tiles it includes must now be red or green. This significantly limits your options. For example, you could make a rectangle out of red and green tiles with an area of 15 between 7 and 3 and 11 and 1, or you can make a thin rectangle with an area. So we can only choose those corners, and we can only count if all of the interior tiles exist. We can't make a box that includes exterior. So we can't choose like this one and this one because that would create a box that includes this upper left area. Using 2 red tiles as opposite corners was the largest area of any rectangle you can make using only red and green tiles. So there's the naive approach of, I guess, filling out the entire grid and then checking every position, which I assume is too slow, but I don't know that it's too slow, right? These are 98,000, 54,000, and it goes down to 10,000. So these potential box sizes are like 80,000 away from each other, 80 or 90,000 away from each other. Looks like they're all between 0 and 100,000. So we'll say that the max distance could be like 99,000 away from each other, or 99,999, right? There are only 500 of them. So we've kind of already established that checking every other position is not too expensive for us to do. We basically have to find all of the triangles as far as I can tell, right? We need consecutive pairs of, or not consecutive pairs, but consecutive triplets where if we mirror it, then that 3rd position or 6th position, I guess, has to also be in range. So it has to land in between 2 items that are on either side of it is really the answer there. I think technically speaking, all of them have to. Ooh, maybe I write some code to visualize what we have, right? We only have right angles. We can basically create triangles from any 3. So where's our full... Right, so if we take this and then vertical here, then we end up with this box where the top left triangle defines this box. And because that is between these 2 in the sequence on the same X value, then this is a valid box. But actually, wait, did I scroll up too high? I did scroll up too high. Okay. Got to make sure to not read part 1 while I'm deciding on how to do part 2. So we have to do it in a place where we have these vertices effectively, which means that I think that this column doesn't count. So all the corners we use all have to be identified. So doing that kind of mirroring, I think, works. We might still have problems with filtering out. But I think the way the problem is set up is basically like if we have this triangle and we mirror that triangle to the other position, then we really only need to test if one position is between 2 other positions. I guess it technically has to be consecutive as well, which I think covers us in the case where it would like turn in or something like that. Using 2 red tiles as opposite corners. It says 2 red tiles as opposite corners, but it doesn't say anything about this triangle situation, right? And it only gives us also singular like columns. I'm just going to kind of assume are not going to be the one that gets us the max area for the moment. There's no example that doesn't use. I don't think that it's guaranteed that you would have the triangle. I can come up with a situation in which if you had like a giant plus sign, right? Right. Let's say, I don't know. It's hard to select these. If we had a situation where I'm just going to ignore what's actually here. If we, let me get a color that people can actually see. If we had a plus sign that looked something like this, right? Then theoretically, we would have like vertex here. And then if we had alternate vertices here and here, then this is a valid box with 2 vertices that is within the area, but does not contain a 3rd vertex, right? Because technically speaking, like this could run like from here down here, over here, here, through, up, down, over. Like this could be the shape, this blue shape, at which point we would have those 2 vertex and only those 2 vertexes. And the heuristic for if they are between sequentials would not work. I think, unfortunately, this is just going to become a matter of checking all the cases. We know like the area already, and we just need to figure out the rules list at that point. So we only have vertical and horizontal edges, which means that, man, I really don't like the idea that we're just going to have to come up with a bunch of rule sets. So I don't think just detecting whether we're on the inside of this or not is enough. We could get all the areas and sort them and start with the biggest area. We could do the calculation for everything. I think calculating the areas is probably fast, and then iterating in reverse max order gives us at least the ability to cull the amount of work we would have to do. Remember, these are like 10, 50, 80,000 long lines. Like what I have here is like 5 long, 6 long, 7 long, whatever it is. There's two things that I can think of because we are kind of like including this border in our area. The vertexes can be on that border if they are right. We've already picked 2 that are on the border. So we don't need to check those. We do need to check the other 2 and see if they're inside. I think we also need to cull if anything in between is outside. This is going to be a bad example here. So maybe, can I clear this somehow? So if we do like this, why is that so small now? So if we like pick these 2, then we end up with 2 quick checks, right? If either of these other corners are not on, or whatever algorithm we choose to use here, if they're outside, then we're done, which is good. I feel like I can't really figure out a way to adjust. So let's talk about the like algorithm that we could do here, right? If this is all green stuff, right? So this is our square. If we have a position, let's do this in blue. If we have a position, right, arbitrary position, and we want to tell if that position is inside or outside this rectangle, if we basically cast a ray towards it, then we've crossed the line once, which means that we're inside. If we were testing this spot up here, and we cast a line from the bottom for some reason, we would cross 2, and because that number is even, then this is outside and thus wouldn't count. So the only case in which that breaks down is if we cross this line, I guess, which needs to be handled specially, right? Because technically we go here, we're in, and we don't really cross another, we're just on. So we have to determine whether we are on a line that we're traveling on, basically, right? Like the one on the right crosses over, it enters and exits on the next, but this one enters and then exits like multiple later. And theoretically we could have, something like this, which would mean that we are on here. And I guess we always have to be on the edge in this case, in this problem setup. So if we are on a vertex and we're moving off, then we also add one. And then this would also be a vertex in this spot right here. So we would add another one and be back inside. So it's just managing all those rules for the constraints that they specifically gave us. And if we do it that way, we would have to find all the lines and basically do a bunch of intersections. I guess at that point we have like a bunch of ranges, right? X ranges or Y ranges. And if we set those up in a data structure that allows us to easily access them for any given point, which I'm not sure we can really do. I guess I could store it twice. The ranges aren't going to be that interesting or difficult. So we could do like the X set, which would be all of the horizontal lines, and the Y set, which would be all the vertical lines. And those ranges would be from here to here, right? X range, here to here, here to here, here to here, here to here. I'm ignoring this extra thing that I stuck on. And then Y ranges are these. And for like the ray cast, so to speak, we would just have to track about whether we've hit a vertex or not, or one of the ends of the ranges. If we've hit an end range, we can skip straight up. It just feels edge casey and I don't want to write it. So the thing that I'm talking about doing here is called point and polygon. Specifically, I'm talking about the ray casting algorithm, where if you end up, like we said here, if you end up crossing a barrier, then the number is odd and therefore you are inside of that shape. And if you are across another barrier, you are outside of that shape. With the additional caveat that Advent of Code tends to have specific definitions for like whether a line is included or not. And these are vertical and horizontal. So there is the possibility or high likelihood that we end up on one of these vertical or horizontal lines. I've used this in previous years, but I think we would have to test every interior point, right? because on the grid, it would be theoretically possible. I don't think it does this, but it would be theoretically possible for it to do something like this, right? And thus, if we had this point, this point, this point, and this point as our rectangle, like this would fill all of those spaces. So we can't just test the edges. Technically speaking, we would also have to test the interior. I don't know if they're being pathological in this question. So we could visualize this and check, but you see how we would have to like test the yellow point, which means testing every point inside of the box, which I think is a significant amount of points, right? If we're looking for the biggest area, let's just find out what the biggest area actually is, right? Let's run part 2 and print out something that hopefully, there we go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So was that a 4.7 billion points for our biggest area? So we would have to run this algorithm for that, which means that we are doing quite a significant amount of work to check that if we have to check every interior point. So I really want to avoid checking like 5 billion points to see if they're inside. I don't think we're going to end up with this pathological case, so maybe we can just skip it. Maybe I should visualize this first, but like this shape, judging from the rules of how this problem was laid out, is a possibility to exist. Like there can be this interior gap, if you will, and this interior square would be the biggest area, but it would not fit. It would not be considered inside. I don't think there's anything in the problem setup that says that this like only turns left or, you know, something like that. The list wraps. Tiles that are adjacent in your list will always be on either on the same row or the same column. Making the shape isn't an issue. We just follow it around. Figuring out if a single point is inside is not an issue because we can just do a raycast. Doing 5 billion raycasts sounds like too many raycasts, especially to check one of the options. So we convert and we write a compute shader. No. There's got to be a better analytical solution. You have to pick 2 of the vertices. I'm just going to keep calling them vertexes because like this is a geometry problem. There's no limits on what this thing can do. It can turn in any direction, which makes it really awkward and makes it so that we kind of have to do the full point and polygon algorithm. 5 billion just seems like too many to do, especially for, I don't know, the 500 that we're doing it on. Wait, that 5 billion number sounds suspicious. Is that actually what we needed? We did area, we got the max. Okay, it is the area. I kind of just want to find out which one that is. So we're looking at 83,000 to 14,405, which is, with spaces required, the right number. So 4.7 billion test for this does not sound like what we should be doing. I guess technically speaking, we only have to check them all if all of them are in. And we could par iter this with Rayon to make it happen quickly. If it's on one of the ranges, then it's in by definition. So we could do a range check, backing up to point and polygon, early exiting if we find any of them that are not in. I feel like I'm caring about the edge cases a little bit too much. I feel like they're not going to do what I think they're going to do. There's just nothing in the problem that says that they aren't going to. Right? Like the way the problem is set up, if I read this generically, this is basically like a game of Snake, and a game of Snake can be in so many board filling orientations. I feel like this is going to turn out to be one of those puzzles where people who skip the entire implementation of figuring out if the interior points are inside are going to be rewarded for it. I just don't want to write all the code and then find out that's not true. Okay, I am just too curious, so I'm going to visualize this. Okay, hopefully this recording actually works. My first recording cut off, which you'll probably see. My second recording didn't record anything but the initial screen on which I started the recording on, which was great. So I lost all of that. And now we are at the point at which I have solved the problem. And I'm going to go back and explain what I figured out and how I figured it out, because basically that cut off all of the visualization that I did. So I have the answer for part 2 here. I think if I remember correctly, that the first recording cut off right when I started talking about doing the visualization. So if we run the visualization, I have since updated it to make it show the appropriate visualization in the center of the screen. This is using Bevy. Bevy is very cool, but you can see the Death Star that this is. If you're unfamiliar with Bevy, it's a whole game engine thing. I've got a startup system and an update system. Everything else is kind of ignorable. We've got the nom parser that we used to pull in the IVEC2s, at which point I just include stir instead of using the asset system or anything like that. Parse it. We get some VEX, we store those VEX for operation on later, and then I set up a camera with some hard-coded values that I reverse engineered from the input. So the input has numbers from like 0 to 100,000, right? And if you're choosing these as X coordinates, Y coordinates, that means everything's going to be in the positive XY quadrant. So I just set those to the size of the window, and I set the center of the camera to be at 50,000 in both, which happens to center the circle because it is a circle. And then we just draw a bunch of gizmos for all the positions. For every position, sequentially, we draw gizmos. So all of these individual lines that you're seeing here are all of the individual lines that show up for the like steps. And the key insight here that I was looking at was, first of all, this is a circle. So we don't really have complicated geometry and thus don't really need to do point and polygon. This can become a massively simplified problem because of the nature of the structure, which leads to the actual part 2 answer. So we've got 2 sets of data. We've got all of the red tile positions, which we need to pick 2 of for the corners of our rectangle. And we've got what I've created here is every line starting at the beginning all the way through to the end and back to the beginning for once. That's why we're using circular tuple windows, because we need to connect that last line just in case. I think it actually wouldn't matter for us in this scenario, but this gives us that extra connection. So we iter circular tuple windows so that it circles back around. I take the length. Actually, now that I think about it, I don't think I need this take. Circular tuple windows being from iter tools. It does look like it stops. So actually what I'm going to do is just remove this take. I thought I needed the take. I was thinking about doing something that was a little bit more cycly, but we actually, I don't think need it. So I'm going to copy my answer here and just run my part 9 answer, not the visualization. And that is the correct answer. So we don't need that take. Circular tuple windows just stops once it connects to the other end. So I collect that into references of I64vec2s. I64vec2s just because we had some size issues in the part 1. These numbers are not actually 64-bit numbers. So we end up doing the collection of all of those individual lines, and then we do the construction of all of the pairs of corners using tuple combinations. We did this in part 1, so we should have already explained that. I sort it by key because I wanted to test the big stuff first. I think with the way that I've actually ended up doing this, it doesn't matter if we sort this by key. Well, it does in my case, actually. It does in my case specifically because I ran find on the end. And we're not doing like a filter for all of them and then maxing or something like that. So you probably don't need this sort, but you would have to change and not use this find, for example. I've basically pre-sorted all the areas, reversed it so that the big one's in front, and then I'm finding the first one that matches these conditions. So we end up with both corners, A and B, for our rectangle, and all of the lines that we created from all of the point-to-point transitions around the circle. For every line, given 2 corners, right? For every line, we compare that line to the lines that construct this rectangle. So we end up checking for if the line is greater than or equal to the maximum right-hand side of the rectangle, right? So if the line is to the right of the right-hand side of the rectangle, if the line is to the left of the left-hand side of the rectangle, if it's to the top of the above, it's to the bottom of the below, and so on and so forth. We do all those 4 checks and return that truthy value, and that truthy value defines whether the lines in this particular problem cause an issue for the rectangle. So I was able to get away from trying to do a point and polygon and trying to test all of the positions by just testing to see if any line intersected, and not intersected technically. I did try to actually write an intersect. Unfortunately, that's in the dead footage that got cut here. I did actually try to write line segment intersection. Didn't end up getting it to work. Came back to it, thought it through again, went with something simpler. But I'm pretty happy ending up with this. I was going to be pretty unhappy if we had to do a brute force of the 5 billion points in the rectangle for some reason. So that's it for today, and I will catch you in the next one. Have a great rest of your day.